Good evening, and welcome to the session on deploying machine learning models for inference at high performance and low cost. My name is Venkatesh Krishnan. I'm a principal product manager for Amazon SageMaker. And today I'm joined by my colleague Rama Thaman, who leads a team of specialist solutions architects who solve key customer problems using SageMaker. We are also super excited and thankful to Matt and Antoine from AT&T. They're joining us today to talk about how they have been able to successfully leverage SageMaker to deploy machine learning models in a highly performant and cost-effective way. So let's get started. Machine learning has become ubiquitous. Our customers are employing machine learning in every aspect of their business, be it in the products they build, in the applications they use, or the business processes they follow. A recent study anticipates that by 2026, nearly 1 in every 3 applications will have some form of machine learning infused in it. So machine learning is no longer an afterthought. When customers have a challenging business problem to solve, or they have an innovation to deliver, they think of a machine learning-based solution from the get-go. So you want to build machine learning into your application, and you have identified the right machine learning model to use, and you've trained it with the best training data that is available to you. Of course, Amazon SageMaker has the right set of capabilities to help you explore your data sets, extract features, and train your machine learning models. Next, you want to put the machine learning models to work. You want to have them generate inference from your live production data, and you want to integrate that inference into your applications. With SageMaker, you can deploy your models behind an endpoint and then invoke that endpoint with a payload or an input through a RESTful API call and get the inference back in response. You can use real-time inference for ultra-low latency predictions, or you can use batch transforms for offline inferencing on large data sets. If your inference requires a large file, such as an image or a video, to run predictions, or if the inference itself takes a long time to run, then you can use SageMaker's asynchronous inference. With SageMaker, you can either deploy a single model, or you can deploy thousands of models behind a single endpoint. You can also jointly deploy the pre-processing step, the inference, and post-processing step, all of these together, as a serial inference pipeline on SageMaker. At the infrastructure layer, you have a choice of deploying your models either on CPUs, GPUs, or you can choose to go entirely serverless. So with SageMaker, you not only get the right model hosting option for your use case, but you also get the best performance at the lowest cost. Excuse me. So when you deploy your models in production, to obtain inference from the model and then integrate that inference into your applications, you have to take into consideration 3 factors. The first is the complexity of the model that you're deploying. So one way complexity can manifest itself is in the size of the machine learning models that you want to deploy. You may have a very large model that you are deploying. The other way complexity can manifest itself is when the payload that you are sending to the endpoint, it's an image or a video file, and that's very large. Or you may have a complex workflow, a pre-processing step, the inference itself, and multiple post-processing steps, and you may want to deploy this entire workflow as a single unit. The second factor you should take into account is the performance requirement from your machine learning inferencing system. So you may have low latency requirements, and by latency, I'm referring to the time it takes to get the inference back from the endpoint from the time you made that invocation. So you may have low latency requirements for real-time use cases. Or you may want to serve millions of inference per second, so that's a high throughput requirement. And most likely, you will want high availability with virtually no downtime. The third factor, perhaps one on top of your mind these days, is cost. There is the compute, storage, and networking cost of hosting your endpoints and hosting your models. But the bigger cost is that of the maintenance overhead, especially when you have to manage the life cycles of thousands of models in production. So with these 3 factors, complexity, performance, and cost, you often encounter a trilemma. You can have your way with 2 of them, but at the cost of the third one. Let me illustrate this with a few examples. If you want to deploy a very complex model, let's say you have a very large model that you want to deploy, and you also have very stringent performance requirements, either in terms of latency or throughput, then you will have to deploy these models on either very powerful CPU-based or GPU-based instances, which will be expensive. On the other hand, if you have cost constraints, if you want to contain your cost, and at the same time you have stringent performance requirements, you may only be able to deploy a very simple model. So you have this trilemma between these three factors, but with Amazon SageMaker, you can get the best performance, best trade-off between these three factors. And let's see how. Let's start with complexity. Recently, large language models have shown a lot of success in performing various natural language processing tasks very accurately, such as entity extraction and text summarization. These large language models are massive in size. We have customers who are training models that have as many as 175 billion parameters. And in the very near future, we will have customers who are training and deploying models that have 10 times as many parameters, 1.75 trillion parameters. A 175 billion parameter model will require at least 175 GB of memory, whereas the GPU in one of the most powerful ML-based instances, the P4D instance, has at most 80 GB of memory per GPU. So there is not enough memory in a single GPU to accommodate the entire model. However, with SageMaker, you can easily parallelize a large model so that each parallel shard of the model can fit into the memory of a single GPU, and the entire model can be hosted on a single machine learning instance. And you can achieve latencies in a few milliseconds, a low millisecond range, and thousands of transactions per second in throughput. SageMaker offers you the option of deploying these models on some of the most performant and cost-effective GPU-based instances, or you can deploy them on SageMaker using the AWS Inference instances, which will save you costs. You can also leverage 500 GB of EBS volume per endpoint to host your models. For applications such as object detection in images and videos, your payloads that you're sending to the endpoint can run into megabytes. And if you send this payload as part of your invocation, then you will take a hit on throughput or latency. For such applications, your best bet is SageMaker's asynchronous inference. With asynchronous inference, you can put your payload into an S3 bucket, invoke the endpoint, and send us the reference to that S3 bucket where you put your input. SageMaker will run the inference, and it will put the output into another S3 bucket and send you a notification via SNS. And this works in near real time with just a few tens of milliseconds in latency. And you save costs as well. With asynchronous inference, SageMaker will queue up your inference request and can scale down the infrastructure to 0 instances when there is no traffic. You can set it up that way. So you don't have to pay when your endpoint doesn't receive any traffic. Yet another way you may encounter complexity in your model deployments is if your application includes a pre-processing step, and it could be multiple pre-processing steps, such as feature extraction, you're generating embeddings, ML inference, and so on. And then there are post-processing steps as well. With SageMaker, you can deploy all components of your application on a single endpoint as a serial inference pipeline. Each application component can be deployed in its own container, and you have the option of either invoking each one of them independently as a direct invoke, or you can invoke them as a serial inference pipeline, which will execute all of them in series. So we talked about how SageMaker offers you the best performance at the lowest cost while deploying very complex models. Let's double-click on this performance dimension, and let's see how you can optimize performance on SageMaker. Applications such as ad serving and personalization often require the inference to be served with just a few milliseconds in latency to facilitate real-time interactions with end users. So you need your inference latencies to be in just a few milliseconds range. Then there may be throughput requirements, machine learning models that are incorporated in applications that serve millions of customers will be required to serve millions of inferences, millions of transactions per second. You need your model hosting platform to have both high availability and zero downtime during model updates, so you have availability requirements. And then there are applications where one model is deployed per end user. These are hyper-personalization scenarios, and you will end up hosting thousands of models and managing their life cycle in production. Now, let's see how you can get the best inference performance from SageMaker. Let's start with latency. Since SageMaker is a platform that is built for high throughput, scale, and availability, you will often encounter a small incremental latency over and above the time it takes to actually run the inference. But with SageMaker, this overhead latency can be as low as 5 milliseconds for small payloads. And you can further optimize this latency by co-locating the client that is invoking the endpoint in the same availability zone as the endpoint itself. How about throughput? SageMaker has a built-in smart routing layer under the hood that will distribute your traffic across all instances that your endpoint is hosted on. So with this, you can scale to serve millions of transactions per second per endpoint. SageMaker guarantees an availability, the endpoint availability of 99.95%, and it will automatically deploy your model across multiple availability zones. And finally, scale. You can deploy thousands of models behind a single endpoint using SageMaker's multi-model endpoints. And with so many options, you have a decision overload. But you do have a friend in SageMaker's Inference Recommender. Using Inference Recommender, you can quickly get recommendations for the best instance to deploy your model on. You can also run an extensive load test to optimize your endpoint for cost, latency, and throughput. In fact, many of our customers have successfully used Inference Recommender to right-size their endpoint, and they have seen up to 30% improvement in price performance. Last but not least is cost, something that's on top of everyone's mind. First, there is the compute, storage, and networking cost, the infrastructure cost. But as I mentioned earlier, the biggest component of cost is the operations and maintenance cost of deploying and managing machine learning models in production. Let's double-click into both dimensions of cost. Using SageMaker, you can easily minimize your infrastructure cost by choosing the right instance to deploy your machine learning models on. SageMaker offers you a choice of over 70+ instances to host your models on, but here are some interesting options for you to consider. So you can host your models on SageMaker using AWS Inferentia instances, and these instances offer 2x higher throughput with 70% lower costs. For models that are typically deployed on CPU-based instances, you may want to evaluate Graviton 2 or Graviton 3-based instances on SageMaker. These instances offer up to 40% better price performance than comparable generation of x86-based instances. And it's always a good practice to set up auto-scaling so that SageMaker can provision and deprovision instances based on your traffic. Another option that will help you save costs for hosting your machine learning models is serverless inference. With SageMaker, serverless inference is truly serverless, which means that you do not have to choose the instances on which you're deploying your models. You do not have to specifically set up auto-scaling policies. SageMaker takes care of that for you. And you do not pay for keeping the endpoint up and running when there is no traffic. With serverless inference, you only pay for the duration for which your inference runs. The only flip side is that you may experience a few seconds of cold start latencies when the first inference request hits the endpoint after a period of no traffic. And this happens especially when the traffic pattern is unpredictable. SageMaker also offers you the option of deploying thousands of models behind an endpoint using SageMaker's multi-model endpoint. SageMaker makes this possible because it will dynamically load and unload models from the endpoint based on your invocation traffic. So if your model receives a lot of requests, that model will be loaded onto the memory of the instance. If it doesn't receive traffic in a while, we will offload that model and load and make room for other models that are receiving traffic. So we manage that dynamic loading and offloading, and therefore you can save up to 90% of your deployment cost if you use this feature. But as I mentioned earlier, the bigger cost is the cost of operations. With MLOps tools on SageMaker, you can achieve operational excellence in deploying and managing machine learning models at scale. You can easily automate the model building process, the model building workflow using SageMaker pipelines, and you can get ready-to-use CI/CD templates via SageMaker projects. You can use deployment guardrails to update your endpoints with newly trained models. So if you're retraining your model and deploying it, you can use deployment guardrails to move traffic from the old model to the new model in a controlled way. So you can move a certain portion of your traffic to the new model. And if that doesn't work well, if you're not satisfied with it, you can quickly revert to the old model. You can monitor models in production using Model Monitor, and you can get online explainability in real time. And finally, you can use SageMaker's model registry to catalog your models. You can use that to track metrics and record and search end-to-end model lineage. So you may be wondering, this is all great, but why can I not build my own model deployment system on Kubernetes and manage it myself? My colleague Rama here will tell you why you are better off using SageMaker instead of doing this on your own. On to you, Rama.
Thank you, Venki. Managing a machine learning infrastructure is not a trivial undertaking. You need a lot of resources to build and manage. Customers who use SageMaker, they're able to focus on building the model and offload the heavy lifting of managing the infrastructure to SageMaker. They're able to innovate through model and enhance their business value. Furthermore, with SageMaker, there's no upfront cost. There's no licensing cost. You pay as you go, which makes it more conducive from a total cost of ownership perspective. Let's look at some of the challenges and complexities that you have to overcome if you're managing the infrastructure on your own. Starting with the infrastructure management at the top, at the foundational level, you need to have a platform that's scalable, reliable, secure, and operationally very performant. On top of it, you need tools that helps data scientists take a model from experimentation to production very quickly. Our customers are able to lower the time that it takes. In some cases, we have seen customers taking months together to get a model from experimentation to production. That's because you need to have the right tool set. It's not about building a model. You need to have MLOps tools deployed to production and so forth, right? So from that perspective, when data scientists are starting with a model, they're going to try different frameworks. They may start with sklearn. They may try XGBoost, deep learning models. They should be able to quickly take these frameworks and test out. If they have to go install or get IT's help, that's when things slow down. So what that means is you will have to manage these frameworks in containers or machine images so that data scientists can quickly take and work with it. When it comes to compute instances, depending upon your use case, you need the right instances. For example, if you have a XGBoost model, you will need a memory-optimized instance for optimizing for cost and performance, right? And in some cases, you may need compute instances, some cases GPUs, right? The important thing is you need to have capacity when you need it, right? In many cases, I've been a CTO for a startup before this. When I need an instance, if I don't have it, then I have to go procure it. That slows down you, right? So that's why you need to have the capacity. That's very critical. So from infrastructure point of view, you can see there's a lot more heavy lifting that you have to do in order to have these containers, these compute instances, to have your data scientists quickly build models and deploy to production. Supporting high availability has its own challenges. So if you look at resiliency, like Venki mentioned, you should be able to deploy a model in multiple availability zones. In other words, in multiple data centers, so that you have resiliency. When one goes down, you have the other one, right? And in some cases, you need self-healing in your infrastructure. If there's a bad instance, you should be automatically replace that instance, right? And more stringent your SLA is, the more complexity your infrastructure will have. With SageMaker, you have 99.95% SLA for real-time inference. So managing infrastructure with that kind of availability comes with a cost, and you need a lot more resources to build something like that. Security and compliance, this gets overlooked often. Many times you will have to comply with SOC, PCI, HIPAA, FedRAMP, right? So you need resources to manage these controls. With SageMaker, you get that out of the box for the infrastructure. It's a shared responsibility where we give you compliance for the infrastructure, and you also get tools to comply with, say, encryption, authentication, authorization, so forth. Cost optimization tooling, that's very critical. Depending upon your use case, you need to have the right inference option. Venki talked about serverless, async, real-time, and so forth. So you need to have those right kind of inference options to lower your cost. And in some cases, you may want to get the best out of what you pay for an instance. You should be able to deploy multiple containers on that one instance that you have. You may have a pre-processing step. You may have an inference step, post-processing. You don't want to have multiple instances for each one. That'll be a lot more expensive. You should be able to put more containers on that instance. In some cases, multiple models behind that instance. That's where multi-model endpoint comes into picture. So you can see that there are different things that you need to reduce your overall cost, right? Once you have a model in production, you need different set of tools to take it to the higher levels, like moving it to pre-prod or production, and being able to monitor the model, right? Once you deploy to production, you want to be able to monitor data drift. Is your data drifting? Is your model drifting? You should be able to track all those and retrain and deploy. So there's a lot of heavy lifting that you need from that MLOps capability itself. And also this explainability, explaining why a model is providing that inference the way it is. And also lineage tracking, being able to track from a model all the way back to the data that was used for that particular model. So there's a lot of coding and the logic that you need there. The last one is observability. You should be able to track the instance resources like CPU, GPU, and so forth. For example, if your CPU utilization is below 50%, chances are you could go with a lower instance of lower cost, right? So you should be able to track all those. And if the instance usage is higher, then you may need to have another instance backing that. So you need those metrics to optimize for your workload. And also there's invocation metrics. Depending upon the number of invocations that you get, you may want to scale up or scale down. You may have peak periods where you need more instances to back that up. So you should be able to track all those, and automatically, behind the scenes, your infrastructure should go up and down. So you can see there's a lot of tools and capabilities that you need in order to take a model to production and manage that efficiently from a cost and performance perspective. So if you look at the total cost of ownership, with SageMaker, you get lower cost structure. You have infrastructure cost. Venki talked about compute, instance storage, and network, and a little bit of operations cost on top of it. If you're managing it on your own, let's say on EC2 or EKS or ECS, you would have the infrastructure cost, you would have the operations cost, and security and compliance cost. You can see the cost is higher if you're managing on your own. I talked about the complexities. Now, let me show you how easy it is to deploy a model onto SageMaker. So here, I have an example. I have a TensorFlow model that I'm deploying. All I have to do is import the SageMaker library. I'm leveraging the TensorFlow model class. I have to specify the location of my model. You could have trained this model on-prem or SageMaker anywhere. And you just put the model in S3, provide the location, then you can deploy by specifying the instance count that you need, the instance type that you need, and behind the scenes, automatically, we will deploy the model for you and give you an endpoint that your applications can run inference against. So that's how easy it's this, like 5, 6 lines of code, and you have a REST endpoint ready for inference. Let's look at a demo. I'm going to show you a demo of multi-model endpoints. So here, I'm going to train models to predict house prices for different cities. For example, a model for San Francisco or model for New York, what have you. And once I have the models, then I will deploy that behind a multi-model endpoint. Before I go into the demo, I'll tell you how it works behind the scenes so it's easy to comprehend. First, building the models, get all the models, put it into a S3 bucket. Here I have for Chicago, Dallas, and so forth. Then once I have the model, then I would specify the location where the models reside and deploy a multi-model endpoint. And I will have an endpoint that my applications, may it be mobile application or desktop application, it can call for inference by passing the name of the model that you need inference from. So that's how simple it is, 3-step process. Right? Now, let's look at that in action. So this is a recorded demo. So for this demo, I'm going to leverage an example that's in AWS samples GitHub repo. And this is under advanced functionality, multi-model XGBoost. And what I'm going to do is take this example, go into SageMaker Studio, and run this example from there. So I'm navigating to my SageMaker Studio environment. You can see I have a user profile there that I'm going to launch. And this brings up a Jupyter notebook for me. And here, what I've done is I've cloned the examples that I showed you. And I can now go into that example, open that notebook, and start running. There are a bunch of other examples that you could try out. So I'm going to go into advanced functionality here, open the multi-model XGBoost example. And here's the example. So here, there are 4 main steps. The first step is to create some data. I'm creating synthetic data for each city. And I'm going to train a model per city. And then once the models are ready, I'm going to deploy a multi-model endpoint, then finally run prediction against this. Right? So let's start with the first step here, generating a synthetic data. You can see that I have about 10 plus cities for which I'm getting data and training models. So that's that first step there. Then I have a bunch of utility methods. You can see I have different features that I'm using, the square footage, the area, and so forth. So these are, I'll generate data for these features. And you can see more utility functions here. And with that, I can start defining my training parameters. So here's where I'm defining the training parameters. Here I'm using XGBoost. I'm going to leverage a container that SageMaker manages, so I don't have to worry about the installation of the framework itself. Then I also can specify the training instance that I need for hosting as well as training. In this case, I'm using the same instance type. And here's a utility method again to split the data for training and validation, right? Bunch of utility methods. And this function here, you can see it uses XGBoost. I have certain hyperparameters that I'm using for training. And so I will now call that function, and I will train the models in parallel. So for 10 different cities, you can see I'm going to run through that. So it kicks off 10 different processes for training models for different cities. And once that's kicked off in the back end, now I can wait for those processes to complete. Usually it takes about a few minutes because the data is not large here. And once I have all the models here, you can see the training is done in this step here. The next step is for me to deploy a multi-model endpoint. The critical thing is knowing where you're storing the model. So that's the location there. And once I have that, now I can deploy, I can use the multi-data model class. Then I would say, hey, here's the location where the model resides. Then the next step is deploying. I'm using one instance in this case. You could have more than that. And I specify the instance type. Then there it is. I have an endpoint that my applications can call for inference. And I can also check, hey, what models are behind this endpoint, and it lists those models, right? Now, let's run inference against these models. So for the first inference request, I'm going to get house prices for Chicago. I'm passing the name of the model for Chicago, and I'm running it. When you run for the first time, you can see that it takes about close to 2 seconds there. That's because it's loading the model to memory. Venki talked about that, right? When you run for the second time, it's lower. It's about 37 milliseconds, right? Because the model is already in memory. It makes it easier, and the inference gets faster. And I'm going to run inference for 5 more cities. You can see first time it takes a little longer for each of those. And I now have loaded 5 different models to memory at this point, right? Now, let me show you some of the metrics from an observability standpoint. So you can see here, if I need to know at that point in time how many models are loaded in memory, I can look at that metric, loaded model count, and you can see I have 5 different models loaded in memory. And also, I can look at CPU utilization, memory utilization, disk utilization, and so forth. That gives you a lot more insights to set up thresholds. When certain thresholds are breached, you get alerted and so forth. And also, I can look at other metrics, such as invocation count. So here, you can see I can look at, hey, how many invocations at any given point in time. And you can also get other metrics from here, like model latency, how long it is taking for an inference request, right? And also, you can look at overhead latency here. So you can see there are a lot of these metrics that you have to track, and that comes out of the box for you if you use SageMaker. You don't have to do the instrumentation of it. That takes a lot of effort, right? And also model loading time. How long is that model taking to load into memory, right? So all of these are important aspects so that you could optimize your models from a loading standpoint. And also, you can see we have a lot more other metrics, like the number of errors you have, and model downloading time from S3 when you get the model from S3. So all of these things will help you in terms of optimizations, right? Now, I'll invite Antoine to talk about AT&T's experience deploying multi-model endpoints. Antoine.
Thanks. My name is Antoine Deflot. I'm a Director of Data Insights at AT&T in our Chief Data Office. I'm joined today by Matthew, who will come up here in a little bit. Matthew is the Chief Architect for USM inside of AT&T Business's cybersecurity product organization. So Matt and I spent the last year or so leading a project to beef up the machine learning capabilities inside of the Unified Security Management product, also known as USM. So we'll spend the next 20 minutes or so talking about what we did on that project, some of the things that we learned. But before we do that, we'll talk a little bit about the product just to situate the work. So USM, or Unified Security Manager, as it's known, is a cloud-based integrated cybersecurity product that we sell to our enterprise customers. USM provides asset discovery, it provides threat detection, as well as incident response functionality. And it's used by several thousand of our customers, both in a SaaS form as well as part of our managed security service that we provide to our customers out of 8 global security operations centers. So a core to the USM threat detection capability is this feedback cycle that you see on the right side here that's centered around our in-house Alien Labs threat intelligence and threat research organization. So Alien Labs, they look at data from across our all the USM sensors that we have deployed in the fleet. They look at indicators of compromise that are uploaded daily into our own Open Threat Exchange platform, OTX. And they combine that with the years of experience that they have looking at threats and looking at cybersecurity issues. And they build these correlation rules that look at events in our customers' networks. And from those rules, determine when it looks like there's been a breach or some sort of a compromise, and generate alarms inside of USM. Historically, these rules have been hand-built. And that's been great for us because that gives us the ability to leverage all the years of knowledge and experience that the Alien Vault, the Alien Labs team has built. But we're looking to see if there's something with ML where we could enhance the types of detections and the types of rules that we're enforcing inside of the product. In particular, we're looking for increased automation, the ability to look at huge amounts of raw data quickly, and maybe come up with some insights that were not immediately obvious or immediately intuitive to a human being, even people like the folks in Alien Labs that have years of experience looking at these sorts of issues. So the project objectives are pretty clear. We're looking to use ML to produce higher quality detections. So a common complaint in IT operations management, it's not just a problem in cybersecurity, is alarm fatigue. So people that are working in operation centers, they get bombarded with all these alarms. It's very hard to tell what's a real alarm versus something that can be ignored. And so we thought that machine learning would be a great fit to help address that problem. Get better quality detections, less alarm fatigue, and allow the experts in the operation centers to spend their time looking at the real issues instead of trying to figure out what's noise and what's signal. And so the way that we wanted to do this was to pick certain event types. So an event type could be an Office 365 login. It could be a Google G Suite document download. It could be an Okta authentication. So we want to create these generalized models for these event types, and then train them for individual customers based on those individual customers' traffic, their specific data. And so in the end, what we would have is a suite of models where customers could benefit from custom-trained, custom-developed models without having to go through the expense and the investment of building the ML infrastructure or building up their data science teams and developing these models themselves. So that's a benefit to the customer. The problem for us to solve was how do we take dozens of event types, dozens of model types across thousands of customers and all the complexity and engineering that comes along with that. So to walk us through that and how we solve that, I'll hand this over to Matt.
As mentioned, my name is Matthew Schneid, Chief Architect for AT&T Cybersecurity USM, and I'm excited to be here and give me the opportunity to tell you about our adventure through machine learning. When designing solutions, it was important for us to keep a few things in mind: cost, complexity, and performance of whatever solution we developed. Complexity-wise, it's very easy to create something overly complicated with all the tools that we have at our disposal today. And so with this in mind, it was critical for us that when we designed our solution, that we needed to keep speed to market in mind, abstract as much complexity away as we could, and allow our engineers to focus on delivery versus developing infrastructure and associated services. Oh, that was not supposed to skip. Sorry about that. I'm just going to use this. Secondary to this, but equally important, was performance of the solution. Our ecosystem today handles burst traffic and high volumes that had to be supported in whatever ML platform that we landed on. We needed sub-second response, global availability, and an ML platform that allowed us to flex on demand. AWS SageMaker checked all of these boxes and then some. In the same vein, you cannot remove cost from the equation. You can design for the best at a premium, but with careful consideration and consultation, you find that you can produce the same product at a cost savings. Thus, it was critical, whatever platform we chose, we had a team that would work with us and through consultation, optimize where appropriate. AWS consultation was key in this regard. They were with us every step of the way, evaluating services and helping us to understand cost placement so there are no surprises. And with that, we're going to take a look at the high-level architecture. What you're looking at is a very simplified view of our machine learning architecture that we worked with Antoine on. We start out with an extraction of customer data via our scheduler microservice, which triggers Glue jobs based on a given customer model type. For those of you unfamiliar with AWS Glue, it's AWS's serverless platform that deals with data integration and has native integration with many services. And it was a logical choice for us for the data movement and cleansing that we needed to do to accomplish for our subsequent steps in the pipeline. When the Glue job is complete, it saves a resulting file to a designated S3 bucket, and the orchestrator microservice in parallel is listening for events on EventBridge telling us that the extraction is complete. When we get the message, we know from associated metadata what tenant and model type we need to execute. The orchestrator does this for us and fires up thousands of training jobs in parallel. We can launch all of those at the same time and not have to worry about the infrastructure or scale. All those concerns are removed via SageMaker. When the training job is finished, When the training job is finished, we trigger the notification via EventBridge and trigger either creation of a multi-model endpoint, or we simply add the model to the already existing multi-model endpoint via a S3 subdirectory. Finally, the orchestrator then records the event it received from EventBridge and updates our system with the new model that was generated by SageMaker. Our microservices automatically updated every few seconds with the new model version, and inference is executed against the new model on the next invocation. Through this architecture, we have serviced tens of thousands of events initially, and then now we're servicing hundreds of thousands, and going into next year, we're projecting millions of events per second. So through the proof of value going into production, we learned a lot. SageMaker, from an MME standpoint, was the most cost-effective solution in implementing what we needed to. We have thousands of models across multiple tenants, and it will continue to grow exponentially. On a per model endpoint, that would have been astronomical cost. Multi-model endpoint allowed us a cost savings, substantial cost savings, and we didn't have to sacrifice any capabilities, which was really nice. With the adoption of any new platform, there were some growing pains. Two of those were utilization of effective auto-scaling from an instance standpoint and ensuring worker scaling at a model level when inference is running at heavy load. It was here that AWS support really shined for us and worked with us through all of that and got us up to where we needed to be to service the load that we anticipated. And you've heard me mention EventBridge a lot through this. EventBridge became our glue for our microservices. And what that allowed us to do was, at any given time, know what was going on in our AWS ecosystem from the time that a job was kicked off to the time that a job was finished, S3 extraction, the whole 9 yards. And we're able to orchestrate around that and deliver models in seconds instead of before it was hours. And very last, use your AWS resources. So support, account representation, they were with us every step of the way, and that allowed us to deliver a proof of value to production in 4 months, whereas originally projected was almost 2 years. And so that was huge for our organization. And finally, before I give it back over to my colleague Antoine, I'd like to give a special shout out to Global Account Manager Nicole Tam, Architect Gaurav Chandra, or as we like to call him, G-Money. He's probably gonna kill me for saying that. And finally, Data Science Specialist Ram Vijayaraju. I'm sorry if I butchered your last name. They have been with me through all of this, and I couldn't have done it without every one of them. Back to you, Antoine.
Thanks, Matt. Okay. All right, so I'm going to spend a few minutes talking about the data science side of things. So, we do get some feedback on the quality of the alarms that we're generating from the security analysts, but that feedback is pretty sparse. And so, generally speaking, this is an unsupervised anomaly detection problem on streaming events. So when in the first generation of models, we looked at using isolation forest and a handful of distribution-based anomaly detection algorithms. In the next generation of models, we're currently looking at using autoencoders or some sort of high dimension embedding search. But for the first round, we went with isolation forest. So isolation forest, if you're not familiar, the way it works is it takes your training data set and then fits a forest of trees to that data set. But those trees, the features that are selected and the cut points are completely randomized. And so what happens when you get a new observation that comes in, you take that observation and feed it into your trees and basically see how deep into your tree you need to go to isolate that point from the rest of the observations. And so the intuition is if this point is an anomaly, it's going to be standing out in high dimensional space by itself, and it won't take very many cuts to isolate that point from the rest of the population. If the point is not anomalous, then it's going to look like a lot of the other existing points. It's going to be buried with a lot of other existing points, and you'll have to cut finer and finer into your data set in order to isolate that one point. So we picked isolation forest because it's easy to understand. It generates compact models, and it performed well in the testing that we did. We use SageMaker notebooks extensively for data exploration, data model creation, model tuning. We use SageMaker processing to build our feature engineering pipelines, and we use SageMaker Clarify in a couple different ways, both during model development, but also on the ML ops side, which we'll talk about in the next slide. So if I was to think about the experience of using SageMaker during this project, I think the one thing that stands out the most is the consistency of the experience. So you're using tools that anybody that's used AWS before is familiar with, using IAM for access management, using S3 for object storage, using VPC, EC2, all these things that people in the AWS environment are just familiar with and comfortable using. And that really helps developers and data scientists accelerate their speed to productivity. So I'll take our project as an example. Matt mentioned this a little bit, but we went from the original estimates on the delivery timeline to get models into production was around 2 years. And so we started the beginning of this year with a proof of concept, and as of this month, so 11 months later, we have 10 models in production. So we better than halved the delivery timelines on having 10 machine learning detection models in production. And that was due in part due to our great team, but also because we were able to use these tools that would just work well together. They're proven, they're well understood, and we're able to build working machine learning solutions very quickly. So I think I hit the laser button by accident. So why don't I go back to 2 ideas that we talked about earlier. The first one was this idea of having one model per customer per event type. And then the other idea is of using SHAP and SageMaker Clarify as a machine learning operations tool, as an ML ops tool. So we, as we were building these models, we had a hunch that because of the way that isolation forest works and because of the number of features that we had available to us, that there probably weren't thousands of meaningfully different models that were being generated. And despite the fact that we had these models in production, we had a hunch that many of these models are fairly similar, and maybe there's an opportunity there to go reduce the number of models, find the ones that are similar, and condense them down. And so we looked to Clarify to try to answer some of these questions. So the first way that we use Clarify and the SHAP analysis output that Clarify gives you is in looking at feature importance monitoring. So basically, you're looking at feature attribution over time, and does it change? So you take some observations out of production, run the SHAP analysis, look at what the feature importance looks like, and then do that again in 2 weeks, in a month, and see if that's changing over time. And if something has changed, then maybe someone should go look at why that's changing. It could be something's broken in your data pipeline. It could be your training pipeline is doing something unexpected. Or it could be that there's an actual change in the behavior of your customer that's being reflected in their data, and that's probably something that you should be aware of. Maybe you need to go retrain your model or reconsider how you set up your models. That was a very useful feature. The other way that we use Clarify was in validation of auto-retrained models. So we have a process that will automatically retrain models and then push those models out to production. In a few cases, we found that for various reasons, the models that were being generated were actually degenerate. And so out of all the features that the model could pick from, it was focusing on 1 or 2 features only, and we saw that right away in the SHAP output. And so if you have some sort of process that is taking a model, retraining it, then automatically pushing it to production, it's a good idea to have some sort of validation in there to see that the model is actually doing what you think it's doing. And feature importance coming out of SHAP and Clarify is very useful for that. Some of these features also exist in SageMaker model monitoring, but we're coming from a place where we had built this into our development work inside of Clarify, and it was a natural extension from there. So if you're following through this, you may be asking yourself, what does feature importance even mean in the context of a model like isolation forest, where the features are picked randomly? So this isn't like random forest or some other tree-based algorithm where at each round you're picking you have a target metric that you're trying to optimize, and you're trying to maximize the purity of each leaf node, something like that. In this case, these features are being picked randomly. So what is a more important feature if they're random? So I would agree that feature importance for isolation forest is not something that comes out of the training process. I would say that it is actually something that comes out of a production operations monitoring process. So if you think about what SHAP does, it's looking at the marginal contribution of every feature value and combination of features and how that affects changes in your model score and your model output. And so SHAP doesn't really care how the model is trained. It's just looking at your model as a black box, feeding features in, and seeing how it changes the model score on the other side. And so I would say, with that perspective, you can definitely take a sample of production data, feed that through a model, and then do the SHAP analysis. And the results that you get are definitely relevant to what's going on with your model. But I think the difference in the interpretation is that now you're not looking at, you're not getting data on what your model is doing on its own or how the model is structured. You're actually getting data on how your customer's data is feeding through the model and then responding. So it tells you more about your customer and less about the model itself. So I've got down here, discovery of model clusters. It's really discovery of customer clusters and how your production models are dealing with the customer's data. But either way you look at it, there's an opportunity here to go from these tens of thousands of models that we were looking at generating and then managing production and narrow those down to a much more manageable set. So that's what we did. And so we have a dozen or so models times a few thousand customers. That's a lot of models to manage. And by clustering these, we were able to actually get down to an arbitrarily low number that makes things much more manageable. So you might be saying, hey, you guys just spent all this time talking about how great MME is and how you guys were able to scale up to all these models, and now you're saying, well, now you got it down to like 12. So coming back to this idea of balancing this three-legged stool of complexity and performance and cost, I think what we learned was that as your models evolve, as your project changes, you're going to have different needs that you're placing on your infrastructure. And having the ability to have your infrastructure and the technology stack you're using flex with those needs is really critical. So the benefits of going down from many, many models to just a few, obviously on the operational side, you reduce the complexity, but it also helps you reduce the ML cold start problem. So different cold start problem than what Venki was mentioning about the cold start of a serverless service. The ML cold start problem is the time period that you have to wait while you're collecting data before you can train your model. And so now having this ability to pull down pre-trained models, look at a customer's data, and then apply the most relevant model to that customer lets us do that on day one of when we onboard a customer to machine learning based detections, as opposed to having to wait for 30 days to do that. Okay, and with that, I'll hand it back to Venki.
Thanks a lot, Matt and Antoine, for sharing your machine learning journey with this audience, and thanks for giving SageMaker the opportunity to help you accelerate your time to value. So with Amazon SageMaker, every organization is able to leverage machine learning to deliver value to their business. It has the right set of tools to enable data scientists, ML engineers, and business analysts build, train, and deploy machine learning models. Again, thanks a lot for participating in this session. Please do remember to complete the session survey on your mobile app. We'd really appreciate it. And we are also available to answer any questions. I think we have 5 more minutes, and we are happy to answer questions. We'll also hang out a little after the session is over if you want to connect with us. Thank you.